In calculus, we had two major topics so far. We talked about limits and we talked about derivatives. In section 4.9, we're going to introduce the antiderivative. The antiderivative is exactly what it sounds like. It's actually the opposite of a derivative. So we look at the definition of an antiderivative. It's going to be some function uppercase f, and that would be the antiderivative of another function, lowercase f, if when you take the derivative of your uppercase f, it's equal to lowercase f. For example, if I have this function, uppercase f, equal to 3x squared, and I want to know if this is an antiderivative of the function 6x, all I have to do is take the derivative of the function 3x squared, which would be 6x. Is that equal to f of x equal to 6x? Yes. So yes, it is the antiderivative. But I got to be careful. Let's look at these next three functions. They all look basically the same. They're all 3x squared, but then they have plus or minus some constant number. If I were to take the derivative of 3x squared plus 1, that's also just 6x. And if I were to take the derivative of 3x squared minus 5, that's also 6x. And in fact, if I take the derivative of any function 3x squared plus any constant real number, I get 6x. Antiderivatives are not unique. So this f of x is not unique. We have a family of antiderivatives for every function, and they will differ by some constant real number. That brings us to this theorem 4.15 about the family of antiderivatives. So to account for this difference, when we find the general antiderivative for a function, we always have to remember to add a plus c for that constant that we haven't solved for yet. So we talked about what an antiderivative is. How do we find the antiderivative? And it just depends on the function that we have. In example 2a, my function is x to the 6th plus x to the 3rd plus x. Now if I was going to find the derivative, I would take the exponent 6 and bring it in front. So I would multiply by 6, and then I would subtract 1 from the exponent. So we're going to do the opposite for the antiderivative. Our antiderivative is, we're going to add 1 to the exponent. So now x to the 6 becomes x to the 7. And instead of multiplying by this 7, we're going to divide, so opposite. So now let's look at x to the 3rd. If I were taking the derivative, it would be 3x squared, but it's the antiderivative. It's the opposite of the derivative. So instead, I'm going to add 1 to the exponent to get x to the 4th, and then divide by 4. Now this x is just x to the 1. Antiderivative would be add 1 to the exponent to get x squared and divide by 2. But we always have to remember that this is a family of functions. So we have to add that constant c. How do I know if I've done this correctly? Well, it's a simple check. If I take the derivative of an antiderivative, I should get back to my original function. And now look, if I take the derivative of x to the 7 over 7, it becomes 7x to the 6 over 7 plus x to the 4 over 4, x to the 4th over 4. becomes 4x to the third over 4 plus 2x to the 1 over 2 plus 0, because that constant is just 0. 7's cancel, 4's cancel, 2's cancel, 0's gone, and I'm back to my original function, x to the 6 plus x to the third plus x. So again, all we're doing is doing the opposite of the derivative. In example B, if I want to find my antiderivative, I'm going to add 1 to the exponent to get x to the 3 halves, and I'm going to divide by 3 halves. Minus 3, x to the 5 halves, I'm going to add 1 to the 5 halves to make it x to the 7 halves, and divide by 7 halves. Minus, remember this 4 is times x to the 0, so the 4 stays, it's x to the 1 over 1. So this is definitely not in simplest form because of the complex fractions. So I'm going to rewrite this as 2/3 x to the 3 halves minus 6 over 7 x to the 7 halves minus 4x. But don't forget your constant c. And this would be my antiderivative. I could easily check that by just computing the derivative and seeing if I get back to my original function. So these functions with exponents, or power functions, they're pretty easy to find the antiderivative. But something like sine of x, that's a little bit odd, right? Because it's not simply adding to the exponent and dividing by that exponent. It's not that simple. You have to ask yourself, if I take the derivative of what function, for what function will I get sine? And that would be cosine. So I know my antiderivative has to be cosine of x. So the derivative of cosine, though, is negative sine. It's not positive sine. So to adjust for that, I'm going to add a negative. And then my constant c. So now let's check, just to make sure. The derivative of negative cosine of x is negative sine x plus 0, which is just sine of x. And that's what I started with. So negative cosine of x plus our constant c, that would be the antiderivative of sine. In this next box, what we're going to look at is we're going to look at some notation. And it may seem like we're complicating things with this notation, but actually we're not. And all of these symbols are going to be needed. You'll find out why in Chapter 5, but for now we just want to introduce it. Instead of just having some uppercase f of x be an antiderivative, we want to be more specific, because that's just a generic function notation. So our antiderivative is going to be equal to this hot mess, which, again, we'll explain what all the pieces mean later on. And we call that an indefinite integral. I will typically always just call it an integral for short. Now, this f of x, this function, is what we're going to be calling the integrand. And dx is what we call the variable of integration. However, since this is an antiderivative, it's actually going to be the antiderivative, right, with that constant c. So when we're looking at this notation, that constant c is what we call the constant of integration. But all of this is exactly the same. It's just another way of writing the antiderivative. When we write it with that weird symbol, which is the integral symbol, we can look at this table of indefinite integrals that you're allowed to use when you're trying to find the antiderivative or the integral. Okay, so let's say that in our integrand, we have our function times some constant. We'll just go with c for a constant. Well, if you have a constant times your function, you're always allowed to bring it out, which is the exact same property that we have for derivatives as well, right? We ignore the constants, we can bring them out. For example, if you're trying to integrate 2x squared dx, and when I say integrate, I mean evaluate the indefinite integral, you can bring the 2 out in front and then find the integral or the antiderivative of x squared with respect to the variable x. So the 2 will stay times antiderivative or integral of x squared is going to be add 1 to the exponent and divide by 3 plus your constant c. Now if you're adding functions in your integrand or subtracting functions, you can separate them into separate integrals. For example, if I was integrating, x to the 4th plus x squared with respect to the variable x, I can write this as the integral of x to the 4th with respect to the variable x plus the integral of x squared with respect to the variable x. And then I can evaluate these separately. Now when you evaluate these two integrals separately, you don't have to write the constant twice. Because we started out with just one integral, you only need one constant at the end. This becomes x to the 5 over 5 plus x to the 3rd over 3 plus a constant. Whenever you're integrating and the integrand is just a number, just some constant number, then the integral or antiderivative is just that constant number times x, of course, plus your constant c. And we've already talked about this rule that says x to any exponent p is going to be add 1 to the exponent and divide by whatever that is. So let's look at the rules for the trig functions. Going back to derivatives, if I were to take the derivative of sine of a times x, so a times x is my argument on the function sine, then the derivative involves the chain rule. I would take the derivative of sine, which is cosine, argument stays the same, it's ax, times the derivative of the inside. The derivative of ax is just a. We're going to do that backwards. If we were going to integrate cosine of ax, instead of multiplying by this a, we divide. So it's 1 over a. And then we get sine of ax, sorry. The derivative of cosine of ax turns out to be negative a sine of ax. So if I wanted to find the integral of sine of ax, I would, instead of multiplying by this negative a, I would divide by negative a. Okay? And it becomes cosine. So general form is that if the derivative of tangent is secant squared, then the integral of secant squared is tangent. And always the a turns into 1 over a. The derivative of cotangent is negative cosecant squared. So the integral of cosecant squared is negative cotangent. Again, remember, we're doing the opposite. Derivative of secant is secant tangent. Integral of secant tangent is secant. Derivative of cosecant is negative cosecant cotangent. Integral of cosecant cotangent is negative cosecant. Let's use these rules that we have to find the indefinite integral of x plus 2 squared with respect to the variable x, which I'll just say dx. That x plus 2 squared doesn't fit any of my rules. Now if it was just x squared, I'd have no problem. But it's an x plus 2 in parentheses that gives me the problem. So what I first need to do is write it in a form that I can use, which means I'm going to be multiplying out the x plus 2 times x plus 2 to give me the integral of x squared plus 4x plus 4 dx. Now this is all addition, so by the rules above I could separate this into 3 different integrals with the x squared plus, this is a 4x, so I can bring out the 4, integral of x dx plus the integral of 4 dx. The first integral would be x to the third over 3 plus 4 times x squared over 2 plus 4x plus the constant c. And then here I would clean it up to be 1/3 x to the third plus 2x squared plus 4x plus c. So that's using all of those properties above. What I would like to note for you is that you don't have to do all of that. Once you get to this point here, where you have multiplied that integrand, I don't expect you to write 3 integrals. It's okay if you just go from that point and just look at each piece separately without writing them separately. So this is what I mean. Look at the x squared. You know that piece will be x to the third over 3. And then look at the 4x. You know that's going to be plus 4x squared over 2. So it's not necessary for you to split this up. If you look at the 4, antiderivative is 4x plus your constant c. And then you would just clean that up to be the 1/3 x to the third plus 2x squared plus 4x plus c. So that's fine if you do decide to split it up into smaller and smaller pieces, but you don't have to, and I don't expect you to. Let's just do some more examples where we're not able to use the properties as they're written. We need to do something more. If I was to integrate or find the integral of 1 over the cube root of x, that's not in my rules. What I first have to do is rewrite this so that this is the integral of 1 over x to the 1/3. So I need to change from radical to exponential form. And then bring that x to the 1/3 up and make it x to the negative 1/3. Once I have it in this form, then I can go ahead and find the integral, because it's just that x to some power, where I would add 1 to the negative 1/3 to get x to the positive 2/3, divide by 2/3, and then add my constant. So of course we can't leave it like that. It's not simplified. This is just going to be 3/2 x to the 2/3 plus that constant. The reason why we call these indefinite integrals is because it's indefinite what the constant stands for. In later sections, we're actually going to be computing what we call definite integrals, and then we can go ahead and solve for that constant c. In this next example, that's crazy. I don't know how to find the antiderivative there. But I do see a lot of trig functions. So that's an indication that I'm probably going to have to use some trig identity. If I go ahead and factor out the sine of x in the numerator, what I have left is 1 plus cotangent squared. And from trig, I don't know if you recall what that is, but that should just be cosecant squared. So this becomes the integral of sine of x times cosecant squared of x over cosecant squared x dx, which is super nice because now the cosecant squareds will cancel. And I know what the integral of sine of x is. The integral of sine of x is negative cosine of x plus that constant. If you're not sure if you have the answer correct, remember all you have to do is take the derivative of negative cosine of x plus the constant and you should get sine of x, which you do. So what happens if you have a derivative but you don't have a function and you want to go backwards and find your original function from a derivative? That's what we have in example 4. We have this derivative, 3x squared minus 5x plus 4. And we're supposed to find the function f. So if we go backwards from the derivative to the function, that means we're going to use the antiderivative or the integral. So our function is going to be the integral or antiderivative of the derivative. Because what happens is the derivative and the antiderivative will cancel each other out and we get back to our function. So this is simply the integral of 3x squared minus 5x plus 4 with respect to the variable x. And I'm sure we're pretty good with finding the antiderivative now. This is going to be 3x to the third over 3 minus 5x squared over 2 plus 4x plus the constant c. And this is where this initial condition comes in. F of 0 is equal to negative 1. So if f of 0 is equal to negative 1, what that means is wherever I see x, I'm going to substitute it with 0. Right? So if x is equal to 0, I have 0 minus 0 plus 0 plus c. Well, all of that has to equal negative 1. We call this the f of 0 equal to negative 1 the initial condition, if I could spell initial. And if you do have an initial condition, what that allows you to do is to solve for your constant c. So notice that all these zeros cancel. So my c has to be equal to negative 1. So going back to my function f of x, I can now rewrite that without the constant c. I can replace that with negative 1 to write 1/3 x to the third. Oops, sorry. It's not 1/3, the 3's cancel. Okay, so that's f of x is equal to x to the third minus 5 halves x squared plus 4x, and now our constant is -1. And that's it. That's our function. Without that initial condition, again, I would just have to stop and leave that c, constant c in there. What happens if we're given a second derivative and we need to find our function? Well, that just means we get to do this twice. So if you're at the second derivative and you integrate, you get to the first derivative. So the first derivative is going to be the integral of the second derivative, which is 4x minus 1. So the antiderivative, or the integral, would be 4x squared over 2 minus x plus our constant c. And we have the initial condition that the first derivative is equal to 0 when x is equal to 0. So because of this initial condition, we know that the constant, after we plug everything in, is equal to 0. So if I rewrite my first derivative, it's simply 2x squared minus x. But I didn't want just the first derivative. I wanted my function, which means I need to integrate my first derivative, 2x squared minus x dx. And that will get me back to my function, which is going to be 2x to the third over 3 minus x squared over 2 plus some constant that I need to solve for. But I have this initial condition that f of 0 is equal to 5. So that tells me that my constant has to equal 5. So my function is going to be 2/3 x to the third minus 1/2 x squared plus 5. This idea of starting with derivatives and working back to the function actually comes up quite a bit. Let's just review our position, velocity, acceleration problems. So we're going to look at these initial value problems for velocity and position. Now remember, our position function was s of t. Velocity we looked at as being v of t. Going back to previous sections, remember that when you integrate, or when you take the derivative of your position function, that gives you the velocity function. And when you take the derivative of the velocity function, you get the acceleration function. So you go from position, derivative, velocity, derivative, acceleration. Well, what happens if you have acceleration and you want to get back to your position function? So you want to find your s of t. Well, I know that the velocity is going to be the integral of the acceleration. So again, this is that idea of working backwards. So the velocity function is going to be the integral of 2t minus 1 dt. My velocity function is 2t squared over 2 minus t plus the constant c. The initial condition is that v of 0 is -3, which tells me that my constant is equal to -3 if I put in 0 for t. So our velocity function is going to be, here the 2's cancel, and I just have t squared minus t minus 3. So to get from velocity to the position function, s of t, you have to integrate the velocity. And integrating the velocity means I'm going to have the integral of t squared minus t minus 3, and I'm integrating with respect to the variable t, which gives t to the third over 3 minus t squared over 2 minus 3t plus our constant. And since my initial condition says that s of 0 is 0, that tells me that my constant has to be 0. So finally, our position function is going to be equal to 1/3 t to the third minus 1/2 t squared minus 3t, and the constant was 0. So we're done. This is our position function. All right, so this is the end of chapter 4. In chapter 5, we're going to be doing a lot of this integration, and we're going to talk more about what that dx actually means and that weird s. So that's it.